Start the recording. So it's being recorded. So yeah, maybe we can start with a little recap. Okay, so let's.
Okay, so at first, let me give the references. Yesterday, I mentioned one reference about the thesis, and let me give some more. So, if anyone is interested more, they can look into this. So, the one is quantum computational complexity from so this one quantum computational complexity from quantum information to black holes and back. This is by Chapman and Polycastro. So this one does not cover about the Krylov complexity, but in general, what is meant by complexity and what is complexity in context of quantum information. So the what I initially told last day, what I said about last day, that state complexity, operator complexity, what precisely does these things means, and there is something called Nielsen complexity, circuit complexity. How does these things come? So that is very well explained in this one, and later they go into the high energy kind of thing, black holes and back, but those are not necessarily necessary for us, but it has a good quantum information part about complexity. So second one is the thesis that I said. And the name of the thesis is this on Krylov complexity. So this is by A.S. Garrido. So this is very well explained. This is like a 350-page thesis. So the only drawback can be that it is so detailed explained that sometimes I lose my focus to get onto the point. So, and there are two reviews. So one is Krylov complexity. This is by Rabinovich and some other authors. So it has a good part about the thing that why Krylov complexity is a complexity. So if I go through the first reference, I will get to understand about the complexity part. What is complexity in general? What is complexity in computer science perspective, and then in quantum information perspective? Why do we care about it? And then this reference 3 discusses very well in its first 3 to 4 pages why Krylov complexity is one such complexity. This all this operator growth kind of thing. So this is one, and the next one is quantum dynamics in Krylov space. This is by Inondi. These are the references and the main paper that introduced Krylov complexity. So that is this one. This one. So this is, I think, PRX by some Parker. So this was the first paper in 2019, 18, 19, and then it started this Krylov complexity business. So yeah, so let me. I am going to at first review the main thing from last day. So that is how we get the Krylov complexity for state from Lanczos algorithm. So I will not talk about the Lanczos algorithm now again. However, so what we had is in Lanczos algorithm, our inputs were a Hamiltonian and a probe vector that belong in that Hilbert space, and outputs are a set of orthonormal basis vectors that are called the Krylov vectors, and these vectors span a subspace of the original Hilbert space that is called the Krylov space, Krylov subspace, and the dimension here n goes to 0 to k minus 1. This k is the dimension of the Krylov space, and here k can be anywhere between 1 to d, and we got two set of coefficients an and bn. So these are the output, and as a result we saw that the Hamiltonian, the input Hamiltonian, could be written in Krylov basis in a tridiagonal form, like a0 b1 b1 a1, something like this. And for our purpose, for Krylov complexity, for calculating the Krylov complexity, we don't need this an and bn. We mainly need this orthonormal basis vector set kn. So how to calculate the Krylov complexity? So so the so So we have initial state phi of 0. From that, using the Hamiltonian, we can time evolve the state and get this phi of t. And we want to compute the Krylov complexity of this phi of t and plot the Krylov complexity versus time. This is the main goal. So we can write phi of t in the following form. So this is just identity, full set of basis vector, and then we have phi of t. So this is the coefficient. We name it phi n of t. So this is just expanding the phi of t in the Krylov basis, and then the Krylov complexity, or called sometimes K complexity. Let me write here Krylov complexity, because sometimes the literature uses the K complexity only for the operator part, and for the state part sometimes they use spread complexity. In these references at some point I have seen, or you can see, that the word spread complexity comes interchangeably with Krylov complexity for state case. But at some places also I have seen something different, state spread complexity. However, these things are related to some extent. uh, Krylov complexity Ck of t. So this is a time dependent quantity and it is defined as sum over so for each phi of t I will get a Ck of t, and then we can do this plot. Here Ck of t and here t. We will get to see mostly something like this. So I will come into this plot. So this is all the Krylov complexity for state. Now,
Will it saturate?
yes, it will saturate, and there will be a saturation value.
Maybe I am wrong, but suppose think we are starting with a state.
Hmm.
Suppose it is zero tensor n. Zero is
Yeah.
any computational basis vector.
Yes.
Then if we evolve this at then at after some time it may go to its initial state also, no?
So that depends on the Hamiltonian using which I am evolving. So
Exactly,
in
that
normal,
depends on the Hamiltonian. So that's why I'm telling that this saturation is not unique.
no, saturation, yes, exactly. Saturation is not, I cannot say for any kind of Hamiltonian it will saturate. For
Hmm.
integrable model kind of thing, it will not, I think, at some cases, it will not saturate. For some integrable model, the saturation value will be less, something like this. So it is
Even
not.
my intuition says that for unitary dynamics,
Hmm.
saturation should not exist. No, why there will be saturation? Because I
Yes,
mean,
I will
if
come into why it is saturating.
uh,
I will come into that.
okay, okay.
So it will saturate for unitary dynamics if it is chaotic, and chaotic dynamics is obviously a unitary dynamics. So for that
Acha,
case, it will saturate.
acha,
So so here what we saw is that to find this Ck of t at each time, I need to find this phi of t using phi of 0 by this time evolution e to the power minus iht, then expand this phi of t in the Krylov basis and collect this phi n of t. However, I can use this tridiagonal structure of the Hamiltonian to come up with the recursion relation for the efficient evaluation of this phi n of t. So that will be computationally beneficial, but theoretically this is what we have to do. So the recursion relation comes like this. So
I have a question. Hello.
yes,
Yeah, so the set is it the reason for the saturation that suppose the state that is evolving once it covers all the points in the Krylov space, it can't spread more. So at
exactly,
some
exactly,
point it has
exactly.
to saturate.
Yes, exactly. That is the reason. And
Mm-hmm.
using that argument, I can find a saturation value and a saturation time. At what time it is saturating and what value it is saturating. I will come into that later. But exactly that is the reason of saturation.
Mm-hmm. And one more thing, since the Krylov complexity depends on dimension, sorry, Hamiltonian and the initial state. So
Yes.
if I have a fixed Hamiltonian, can I always get the initial state such that the dimension of the Krylov space would be minimum?
It depends on the Hamiltonian. It is there can be Hamiltonian for which, if I take let's say one initial state, my Krylov space dimension will be very low. if I take a very particular unique kind of initial state. But for a generic initial state, like in computational basis, let's say all zero kind of thing, I will get a bigger Krylov space. Normally for chaotic Hamiltonian, what happens, that is the main target of to study the chaotic property, one of the main target. So in that case, for any typical generic initial state, now this is very vague term, what is typical generic initial state? So any state that is very normal, that is all I can say. The literature also uses these kind of things, like all zero, all one, or let's say 0 1 0 1 0 1 kind of thing. So in this case, I will see if the Hamiltonian is chaotic Hamiltonian, then mostly the whole Hilbert space will be covered. So the dimension of the Krylov space will be equal with the Hilbert space. And in those cases, unless I take very what, like let's say I take a eigenstate of the Hamiltonian is also a state in the Hilbert space. So in that case, the dimension of Krylov space will be 1, because I cannot generate any other state. So let's say I am taking any other state, some combination of 3 eigenstates. So in that case, if I take 3 eigenstates, the combination of 3 eigenstates at my psi 0, then I will see the dimension will be 3, because by evolving I will get only remain only those three states. So unless I take something this kind of particular choice, so for a generic case it will almost always be equal with the Hilbert space dimension for chaotic Hamiltonians.
Okay.
Yeah, so the recursion relation, so yeah, so the Schrodinger equation is like this. Now, so the tridiagonal form that we had Hamiltonian, using the tridiagonal form, I can write the Hamiltonian in the following way. So this is just writing the Hamiltonian. So these are the diagonal terms. And these are the Bn that was above the diagonal and just below the diagonal. So this is my Hamiltonian. And I can always write the phi of t in this way. So if I just put this Hamiltonian and this phi n of t in this equation, I will get something like this. This is just two-line algebra. So this is the recursion relation. And we will have some boundary conditions. So phi minus 1 equal to phi k equal to 0. And we have a initial condition. This. So my phi n 0. So this phi is a column vector or a row vector, however I write. So when time is 0, then there is only the first coefficient is 1 and all the rest coefficients are 0, because then the state has not evolved along the Krylov chain. So phi n of 0 is like this. So this is not phi n, this is phi 0, and the 1 is the first index. So it's like this. So using this and this boundary condition, I can avoid, what is the point of using this? I can avoid always this exponential. So here to find this phi of t, I had to exponentiate always e to the power minus iht acting on phi of 0. So I can avoid this. This is only the plus point. But theoretically, that is also fine. So what is the typical behavior? The saturation value kind of thing. So from here on, whatever I am going to say, this typical behavior and exponential growth or saturation, there is no, at least I have not seen any concrete mathematical proof of these behaviors. So mainly these are numerical results that have been justified using some arguments. At some cases, they have some analytics. At some point, they do something, they conjecture something. So using those all things, these results are like this. So however, there is no universally accepted mathematically proved behavior. So yeah, so typical behavior of Krylov complexity is like this. So at an early time, yeah, so to see this typical behavior, normally what we need is k is equal with the d. D is the Hilbert space dimension. So what I said, for a generic typical initial state, if I construct the Krylov space, I will see that the k is equal with d. So in that case, the Krylov complexity shows behavior like this. So there is a early time exponential growth. So this is like this. So it is of order very low. Let's say, I think this is of order log n. Log n is, or n is the number of lattice sites, something like this. At least for operator case, this is the case, log n. So for state case also more or less like this. So for reasonable number of lattice site that we normally calculate, 15, 20, 25, 10, whatever like this. So this range is like maybe sometimes range 1 or say 5. So at that time, t equal to 1 or 5, I'll see a exponential growth like this. So then there is a intermediate time linear growth. So this time is of the order of Hilbert space dimension. So initially there was a, so in now the exponential growth is like this in a very small part, even smaller than that, maybe like this. And then I will see a linear growth like this. And then we have late time saturation. So you see the growth is only till the Hilbert space dimension, which is equal with the Krylov space. So at this time, what you said last, now the Krylov vector is now spreading in the Krylov chain. So Krylov chain means this is called the Krylov chain, K0, K1, K2, K3. This list is called the Krylov chain. So there are k such vectors, and when I am around the with time I am around the Hilbert space dimension. So now the chain is, the state vector is now spreading with the Krylov chain, along the Krylov chain. But when the time is of the order of Hilbert space dimension, all the Krylov vectors have been reached. So then there is no vector left that I need to go, that is left to reach. So now the complexity will not increase. So it will saturate. So let's say this is K. So initially a very small exponential growth, then a linear growth, and then saturation. So this is the typical behavior.
Hello, can you
Yes.
please elaborate a little on what you just said? Meaning of what is the meaning of getting to K vector, or like exhausting the space kind of thing?
Yeah. So let me just think. How should I tell? Uh, mm, yeah. So let's say my vector, initial vector was phi of 0, right? So using that, I was creating the Krylov vectors. So I was creating K0, K1, K2, those kind of things. So now I am time evolving this phi of 0, and I am getting phi of t equal to e to the power minus iht phi of 0 equal to phi of 0 so just ignore the plus minus kind of thing, plus some h square t square. So let me give it like this, all the coefficients. This is the main thing, plus h cube t cube. So this is like this will go on like this. So for small t, very small t, all the higher order terms will not contribute more. So I am very near let's say these two vectors are contributing, phi of 0 and h acting on phi of 0. So phi of 0 is what? My k0. I mean, at least I was constructing this k0 from phi of 0 upon normalizing, and this h acting on phi of 0 was giving me k1. So when t is very small, so this k0 and k1 are the only two terms that are contributing here. So in the Krylov chain, so that I was constructing in phi n of t whole square. So where this phi n were like this, so phi of t equal to sum over phi n of t kn. Yeah. So here only k0 and k1 are significant. So that means only phi 0, phi 1 are significant. So here also in this expression, only n equal to 0 and n equal to 1 are significant. So my ultimate value ck of t will be very low. However, when time increases, let's say t to the power 10, when t to the power 10 is significant, then h to the power 10 acting on phi of 0, this is also contributing, which is k10. So k10 if comes into play, then that means my phi 10 of t, this one is also significant. Then in this expression, 10 times phi n of t will contribute, right? So then I am going to get a larger value. However, I cannot, like, for very large t, when let's say h to the power 5000 acting on phi of 0, it will not give me k 5000, because that is not the dimension of my Krylov space. So in that case, it will stop at some point, and then it will just uh, keep keep mixing along all the previous Krylov vectors when all the Krylov space has been accessed. So in that case, let's say that is 500. So then in my expansion, this Krylov, this expansion, always n runs from 0 to 500. And this thing just changes. So n is always 1 times somethings plus 2 times somethings plus 3 times somethings till 500 times something. So only this coefficient changes among themselves. However, this 1, 2, 3 are always same. I am not increasing any more term here. So this coefficient changes in a certain way that this whole term that does not change. So Ck of t saturates. Oh, not a vector. This Ck of t saturates. Is it clear?
Yes, a little bit it's clear.
Okay. You can just think about it later. This is very intuitive and very easy to follow. However, if you just think a bit more, initially I was also not sure why it is saturating. I knew it is saturating. I started coding. I was doing all kind of things. Later I thought about this, and this is why it saturates actually. So yeah. Now the saturation value. So saturation comes when the initial seed vector has spread equally among all bases in the Krylov chain, right? So then this should be equal for all n. So it means in the basis, in the expansion in the Krylov basis, all the bases has equal probability. So just slightly those are changing, but almost equal probability. So that is the case when the state has at most spread. The most spread can come when all the bases has equal probability. So what should be the probability in that case? Then mod phi n of t whole square equal to, there are k bases, so it should be 1 by k. So Ck of t so this mod phi n of t whole square is 1 over k. So I am just taking out 1 over k, sum over n equal to 0 to k minus 1 n. So this is so yeah. So k times k minus 1 over 2, which is k minus 1 over 2. So for large k, which is equivalent to k by 2. And the saturation time is very easy. So saturation time should be, saturation time means at what time I am saturating. So this t set, this is my saturation time, and this is my saturation value. So saturation time should be equal, almost equal with the Hilbert space, the Krylov space dimension, which is in turn equal with the Hilbert space dimension in most cases. So yeah, so this should be K and the saturation value should be K by 2. However, see, this K by 2 saturation value is achieved when the state has been spread equally among all the Krylov chain, all the Krylov bases, and the dimension of the Krylov basis of the Krylov space is equal with the dimension of the Hilbert space. Now it is, yeah. Yeah, so the dimension of the, so now it is conjectured or it is expected that this saturation value will be reached only for maximally chaotic systems, because these two property that a typical initial vector should connect all the basis vector of the Hilbert space. Meaning if I just start from this kind of state, any generic state, and I keep on evolving with H, so I should in principle get all the vectors of the all the I should span all the Hilbert space, and after that the probability when I construct the Krylov basis vector, and I time evolve the state and expand that in Krylov basis vector, all the basis vector will have equal probability. These two conditions are satisfied only for maximally chaotic systems like SYK kind of thing or random matrix kind of thing. So in literature, the those who have worked on this, they have verified that for this kind of models, this kind of systems, the saturation value is almost reached. However, there can be case like this for a chaotic system. Let's say this is my K by 2. This is the saturation value. I am getting something like this. So this is low. I can get something like this. And it has been shown that for integrable cases, this saturation value will be lower. So this is where the all the ambiguity kind of things comes, because these things are not settled yet. So there is no fully proved behavior for integrable and chaotic Krylov integrable and chaotic model. So in general, it is expected this will be chaotic, and this will be, if I can say, less chaotic. So I'm putting this in a comma, colon. So maybe this will be integrable. So this has been shown for XXZ kind of model. So XXZ is a integrable Hamiltonian. However, if I add an impurity here with a coefficient, let's say delta times Z, any zk in a single site, so this model becomes chaotic. So I can just vary this delta. So for delta equal to 0, this is integrable, this model. So this is my Hamiltonian, and for delta equal to say 1 or something like that, it is fully chaotic. Not fully, let's say it is chaotic. And in between, I can show, I mean, it is shown that as delta increases from 0 to 1, the model gradually transforms from integrable to chaotic. So it's not a phase transition kind of thing. It gradually changes. And in that case, the plot becomes like this. So this is K by 2. Let's say this is delta equal to 1, that is fully chaotic. See, there is a gap here, and this gap is bigger than that. I have almost closed the gap, but the gap is bigger. And with increasing value of delta, with decreasing value of delta, let's say this is 0.8, this is 0.7, like this, and this is 0 delta. So this result that I am saying, this is not for state, this is for operator. However, the physics is same for Krylov complexity for state or Krylov complexity for operator, is more or less same behavior, and this behavior is for operators. So just let me give the paper. If anyone is interested, they can look into the operator into the paper. 1 second. Yeah. So this is the paper by these people. So there they have discussed this XZ model, and in the I have discussed the state complexity part. However, they use the operator complexity and they show this behavior. However, it is also said at some papers that for uh, strongly interacting integrable models, I don't know what that is very clearly. Strongly interacting integrable models. This bound can be reached. So initially it was suspected that it will only be, just 1 second. Huh? Yes. So for strongly interacting integrable models, this bound can be reached. So yeah, these things are there. Things are not completely settled yet. And yeah, so still now, these are the open problems. So initially, Krylov complexity was generated for operator case, and the main goal was to see the operator growth kind of thing. So to study the operator growth, normally this OTOC, information scrambling, this operator scrambling, these kind of things are studied, and how a very local, simple initial operator uh, under the Heisenberg time evolution becomes a more complex operator. So that is studied by this OTOC, information scrambling, Krylov complexity, all this kind of thing. Later, they also saw that yeah, this Krylov complexity can be used as a probe for chaos, as a probe to distinguish between chaos and integrable models. However, that part is still open. There are some behavior that are seen for integrable cases, for chaotic cases. So, but exactly how to distinguish between these two, if I have two model in my hand, I don't know which one is integrable, which one is chaotic, whether both are integrable or not. I want to use this Krylov complexity as a measure, then I cannot do that. As far as I know, I have seen that I cannot do that. For that purpose, like this spectral form factor or level spacing distribution, or level spacing ratio. Those are the things that can clearly say this model is integrable or this model is chaotic. But Krylov complexity cannot say that, at least as of now that I have seen. However, the importance lies in the fact that all the things that I said, those are used in distinguishing between chaotic and integrable models. This spectral form factor level spacing distribution using that Wigner Dyson or chaotic or Poisson kind of thing. Those for those cases, I need a clear Hamiltonian, and there are cases where I cannot apply these things, this spectral form factor or level spacing distribution. So in those cases, Krylov complexity can be applied. So I can plot the Krylov complexity. So if I get any formalism comes up in near future, how to distinguish clearly between a chaotic and integrable Hamiltonian using Krylov complexity, then we can access much more model that can be said whether it is integrable or chaotic. And another fact is this thing becomes so popular from the high energy community. So there must be some reason, I don't know what, but that they apply this thing for black hole physics, complexity of a black hole, a initial operator in a black hole, how that becomes more complex, this ADS CFT correspondence in CFT theories. So in that cases, there must be some reason this Krylov complexity has gained much attention, and there must be, maybe that is because the other probes like what I said, spectral form factor SFF or level spacing distribution, maybe these are not applicable there. However, now recently, this Krylov complexity has also been studied from condensed matter or quantum information perspective, or recently in circuit perspective also. So, whether a circuit is chaotic or integrable, or what is the situation, so these things cannot be said using this SFF, spectral form factor or level spacing ratio. In those cases, this Krylov complexity can be a very good potential indicator. So that is the point of studying this. So now I will come into the Krylov complexity for operator case. So the initial reference that I said, this last one, this 5, a universal operator growth hypothesis. This was in 2019, 18 or 19. So in this paper, they first mention about this Krylov complexity thing. This definition that I said, that I showed, n mod phi n square kind of thing. The expectation value in phi of this Q operator that I last did. This kind of thing, they first appeared in this paper. So, however, this Krylov method, Krylov construction, this Lanczos algorithm, these are all the things that are required to come up with this quantity. Those are long before in the literature from 1930s. This is the Lanczos algorithm is there, and in this paper initially they discuss about the operator Krylov complexity in context of operators. So I think they also discuss states, but the main point was for operator. That is why the name is universal operator growth hypothesis. And they hypothesize something there, how a operator grows. Uh, and later it got translated into the state picture also. However, I started from the state because the state is more easier to follow. At least for me, it was more easier to follow. So Krylov complexity for operator. So it gives an idea about operator growth along the Krylov chain. So let's say my O of 0, this is an operator that belongs in the operator space. So some notation here, my Hilbert space is this. This curly H, where states lies, and the operator space is the space where all the operator that acts on this Hilbert space lies. So operator space is this with this big hat. So this is my operator space. So an operator belonging in the operator space, and it has dimension d square, because that is also obvious. If the Hilbert space has dimension d, then the operator space will have dimension d square. So in Heisenberg picture, the time evolution looks like this. So O of t is e to the power so this is the time evolution, and I can expand this using the BCH formula, Baker-Campbell-Hausdorff formula, that is like BCH, that gives e to the power S A B e to the power minus S A equal to B this. So using that, I can expand this one. So I will get this. So now let's denote L as the it is a super operator. Super operators means it acts on an operator and gives back another operator. So just like functional in classical mechanics, where it acts on a function and gives back another function. So this is a super operator. So the action is like this. So L acting on some quantity gives back commutator with the H of that quantity. So this is the action. So if L is acting on this O of 0, so O of 0 is the operator. This L acts on that and gives back the commutator with H. So this is also an operator. So this is the action. And this is called the Liouvillean. So then this line becomes like this. O of 0 plus IT, L acting on O plus IT whole square by 2 factorial, L square acting on O. So L acting on O gives a commutator with this HO. Then again one L acts on that thing that gives commutator with another H with this thing. So it goes on like this, which is nothing but the exponential. So they write the T here. You see, I have appeared at a picture like the Schrodinger case. This looks like that. And in Schrodinger case, Schrodinger picture, I normally denote the state in Schrodinger picture. The states are denoted like this angular bracket. So in Heisenberg picture, we are going to represent, so this is my space, this. So here it was in this Hilbert space. So here we are going to denote the operator as this, with this first bracket, right? And this lies in the operator space. So you can write this like this: O of t equal to e to the power minus ITL acting on O of 0. And this can be written as just the last equation in a summation form. Summation n equal to 0 to infinity this. So normally in Schrodinger picture, Hamiltonian is called the generator of time evolution, generator of the time evolution in the Hilbert space on a given state vector. So here also, this curly L is generator of time evolution of operators. Same, just the like same kind of thing. There we had psi of t equal to e to the power IHT psi of 0. So here we also have O of t equal to e to the power ILT acting on O of 0. So there we had this Hamiltonian as the generator of time evolution. Here we call this L as the generator of time evolution of operators. And here previously what we had is we had a notion of inner product. So we knew what is psi of t, phi of t, how to calculate these things. So here also I must have an inner product between two operators in this new operator space. So the inner product is defined like this. So let's say this is A. This A and B are two operators, and it will be 1 over D trace of A dagger B. This D is dimension of the Hilbert space, not the operator space. Hilbert space means the dimension of the state space. So this is the inner product. So naturally what follows is, in state case, we acted by H on phi of 0 to get the Krylov chain. So that was like phi of 0, then H phi of 0, H square phi of 0. So similarly, here we apply with the Liouvillean H. And we apply it on the operator. To generate the Krylov chain. So here This is the Krylov subspace in the operator case of the full operator space. We denote, we give a zero, O of 0 in the suffix to just denote that it is generated by this initial seed operator. So this is defined as O of 0, L acting on O of 0. This. So here also by construction, this H O, this is a subspace of this full H, and we had for space state case dimension was 1 greater equal to K, lesser equal to K, lesser equal to D. This is for state case because D was the Hilbert space dimension. So similarly here its dimension should be 1 K D square. However, there is a stronger bound here. So see here this is the bound that I can get. Here, this is the bound I can say from construction. The dimension cannot be greater than D square because this is a subspace of the full operator space. So maximum it can go is 2D square. So however, there is a stronger bound here. So to get the stronger bound on the Krylov space, we do the following calculation. Let me just say first what we will appear at. So we'll show that 1 D square minus D plus 1. So this is the stronger bound. So I could have just said the bound, but however the proof will be necessary to understand the circuit case that will be discussed later maybe. For brick wall kind of circuit or any kind of circuit when we implement, in that case this will be very important. So that's why I am going through the proof. So yeah. So the proof will be done using by constructing this matrix at first. So from now on, I am just writing this O in place of O of 0. So this is equivalent with just O. Whenever O of t appears, I will write O of t. So this O, L O, L square O, L cube O. In this way, I keep on adding. So I have to construct this matrix. However, here O is not just, it's not like I have written the full O matrix here, then I have written the LO matrix here. So this is not this. So what it is like this. So on the first row, I write all the elements of O. So O has D square element, this has D square element. So I write all D square element on the first row like this. O11, O12, O13 till O1D. Then O21, O22. In this way, I keep on going till ODD. Okay. Then in the second row, I write the LO is also a matrix. It's 1 component. Then LO 1 2 component. In this way, LO it's DD component. So the column of this matrix is D square, the number of column. So this O, so because I am writing all the elements on a single row and the number of elements is D square. So the number of column in this big matrix is D square. And the number of rows, this is the number of rows that depends till what value I am going to take. So if I take, let's say, L to the power, so this is L to the power 0 for uniform convention I am giving it. So if I take L to the power 10, so the dimension will be 11. I am starting from 0. So let's take L to the power d square minus 1. Okay, acting on O. So I will take till that position. So what will happen? D square minus 1 starting from 0. So there are d square rows also. So it has d square row by construction, and it has d square column. So this is a square matrix, and this matrix is called this Vandermonte, I think, Vandermonte matrix. And what they say is, by finding the rank of this matrix, I can find the dimension of the Krylov space. So this part I understood very vaguely, not vaguely, but very intuitively. So I don't have any words to say how the rank of this matrix is giving me the dimension of the Krylov space. So this is a square matrix of d square cross d square dimension, and the rank of this matrix will give me the Krylov space. So it can be understood like this: the rank actually comes from number of linearly independent vectors of a matrix. So if I have a matrix like this, where these are, let's say, the columns, if two columns are linearly independent, two columns are linearly dependent, then I cannot get the full rank here. So rank will reduce. So however, if all the rows, and all the columns, if these are linearly independent, then the matrix will be a full rank. The dimension will be equal with the rank. So here also, see, I am constructing L acting on O, L1 acting on O, L square acting on O. I need to find till what position these are linearly independent, right? So that is the number of dimension of the Krylov subspace that is being generated. So this is just written in this way. So if I can find the rank of this big matrix, that will give me the number of linearly independent vectors in this big matrix, number of linearly independent rows or columns, let's say. So that is in turn somehow giving me the number of number of bases in the Krylov subspace, or the dimension of the Krylov subspace. So yeah, so the matrix that I wrote, so yeah, so now I will write this matrix again, but before that, this big matrix, before that, let's see something. So in state case, normally we can expand the operator in a certain basis, let's say eigenbasis. So for Hamiltonian H, let's say I have basis En, the eigenbasis, right? So we have this superoperator L. So I can have any basis, and this basis lies in the Hilbert space. So for L is the super operator, and for this super operator, the basis will be operators. So H is an operator. For that case, the bases are states. So for super operator L, the basis will be operators. And let's say the bases are written as omega AB. Okay. Here n goes from 1 to D. D is the dimension of the Hilbert space. Here A, B both goes from 1 to D. So in turn there are D square, since there are two indices. So there are D square bases, and that is normal. There should be D square bases. So we take a choice of the basis to be like this. We take omega AB to be EA EB, where this EA EB are the eigenstates of the Hamiltonian. So this thing is an operator. right? This EAEB is a operator. So I am taking this kind of form to construct the basis of the superoperator Liouvillean, this L. So there are d square such terms, and I can expand any operator in this basis. For Hamiltonian case, just like I can expand psi, let's say not t, psi equal to sum over n equal to 1 to d cn en. I can expand like this. So here also, in operator case, I can expand this O, a general operator, as sum over AB, OAB, omega AB. Right? This omega AB are the basis vector. This OAB are coefficients. AB runs from 1 to D. So there are D square such coefficients. So let's see the action of L on omega AB. So the action of H on EA is EA, EA, where EA is the eigenvalue of that eigenstate. So let's see how the action of L goes. L acting on omega AB. So what was the action of L? Action of L was defined as taking a commutators with H. So it will be like this. I had defined the action of L on anything is it takes commutator with Hamiltonian. So here the action of L acting on omega AB is it is taking the commutator of the Hamiltonian with omega AB. So it means H acting on omega AB, where omega AB is again, I am writing that EA EB minus omega AB H, where omega AB is EA EB H. So H acting on EA will give me EA, the eigenvalue, and back EA, where EA, that means again omega AB minus this H acting on EB will give me EB, and then EAB back, so that will be again omega AB. So this is EA minus EB omega AB. Right? Now AB, and let's write this as omega AB. So L acting on omega AB equal to omega AB, omega AB. So there are d square eigenvalues. Note that d eigenvalues are 0. At least d number of, so let's put a at least here. At least d number of eigenvalues are 0. Since this omega AB equal to EA minus EB, so whenever A equal to B, this gives me 0. And A equal to B, there are d values of A, d values of B, so there are d values of EAB, so there are d such cases. So there are d 0 eigenvalues. Okay. So and those are like omega AA. Omega AA. These are 0. And if we see L to the power n acting on O, that will be AB equal to 1 to D. So just I am writing at first the O, AB, omega AB. Right? This is just the O that I had written before. This form, O equal to this. So now if I apply L on that, L to the power n, so acting on this omega AB, I will get just the eigenvalue omega AB, and I am applying n times. So I will get omega AB to the power n. Okay. So now I can separate this as with A and B. Okay. So let's say I am writing when A equal to B. Then A equal to 1 to D O A and omega, let me write it, then I will remove omega A to the power n omega A plus A not equal to B and AB starts from 1 to D O AB omega AB to the power n omega AB. Now this omega AA is 0. So when this first term will be non-zero, when n equal to 0. So when n equal to 0, then I am not applying any Liouvillean here. So there is no L to the power n. So then I don't have this omega AB eigenvalue in front of. So if there is no omega AB, then there is no point, it is not going to become 0. So there is a delta n0. So when n equal to 0, then these terms become non-zero. And then this is just 1. So I am removing this. Okay. So it will come into action later. It will come into action now. So this is the action of L to the power n acting on O. So let me just. Yeah. So using this, let's now write the matrix that we are writing. L to the power 0 O till L to the power d square minus 1. So we are taking d square minus 1 here till make it a square matrix. And just initially I said the highest dimension can be d square. So if I construct a d square cross d square matrix, so that is enough. If the whole dimension, if it is a full rank, then the dimension turns out to be of Krylov space to be d square. So this L to the power d square minus 1 starting from 0. So there are d square such elements, and the matrix will look like this. So initially we have O11, O12 till O1D, then O21, O22 till. So in this way I am going till ODD. So there are d square elements here. Then the action is L acting on O. So what was L acting on O? Yeah, L acting on O is this. I will get from this. So these are just the coefficient, right? So this O11 is just coefficient of omega 11, omega 11. Right? So next here will be the coefficient of this L acting on O. Then from here the coefficient. So that means this. This is just like the state case, nothing else. Just how we construct a matrix. So it will be omega 11, O11, omega 12, O12, omega 1D, O1D. Then omega 21, O21 till omega DD, ODD. Then it will be omega 11 square, O11, omega, sorry, this is omega 12 square, O12, omega 1D square, O1D, omega 21 square, O21 till omega DD square, ODD. Okay. So in this way, we will have omega 1 to the power d square minus 1 O11.
This is the last one you plan to speak about, right?
Yes, when I arrive at the dimension, that will be last today.
How much time roughly?
Maybe 3 to 4 minutes.
All right, all right, all right.
Otherwise, if you say I can stop here also, I can start from here.
What is the, because anyway you have to repeat a little bit, right?
Yeah.
Maybe then we can start from here. Okay, because I think it's more than 1 hour, so people will be
Yeah.
little hungry. So anyway, we can again start from here. So unless there is any immediate questions, so you can ask the people who are still there. If you have any question, maybe.
No such question. Matlab, the algebra was I was understanding the algebra, but too much content for today. I have to absorb a
Okay.
little.
No, that's important.
Yeah, yeah, okay.
Not
Mhm.
like a regular lecture. Okay, so maybe we can stop here. But what about tomorrow? Or are we having it tomorrow, or what you are suggesting, or next week?
Yeah, I can give tomorrow or next week, whatever everyone is comfortable with. I don't have any problem.
So maybe because anyway you are giving online. So I
Yeah,
would suggest maybe take a break. So let the people, let's grab this 2 lecture content. And
yeah,
maybe next week we can come back.
yeah, okay.
Because today I was a little bit involved, so maybe otherwise there will be no point if there's no question, right? So we're not having a formal teaching. So maybe next week. So I will again email. Then if you get time, you can just go through this, and we will share the notes, and then so we are left with maybe maximum 1 lecture, I think, right?
Yeah, one lecture is also not required. I mean, I
Right.
need
Okay. So we
maybe
may
20,
squeeze it to
30
one
minutes.
hour, something like that. Okay, or we can have
25 to 30 minutes is enough.
right, right. But again, so then for the others, maybe it's better if you just come up with more questions.
Mm-hmm.
Okay, especially the MSc students. Okay, okay. So let me then stop here. And I will again, thanks for joining again, and I will send the information again. Okay, when we will have it. Thank you so much. Okay.